We have a bit of pressure, because after this we'll have a coffee break, but not just a coffee break, but a coffee break with an enjoyment of posters, which is just around the corner over there. But that means that this session has to preferably stop on time. And that's why I say we start. And we start with Andre Tejo. I found out how to, after working like 3 or 4 years together, how to finally properly pronounce your second name. And he's from University of Groningen. We work together quite a lot. And specifically in this talk, we usually, when people look at the AI models, we have like high accuracy, but at the cost of energy, or low accuracy, and then energy a bit less. And we find out that maybe that's not always the dilemma we have to solve. So Andres, please, the floor is yours.
Hello. Good afternoon, everyone. Thank you for attending my session. So today I'm gonna basically talk about our approach to foundation models and how we work to make them sustainable at the end. So now we are bombarded by foundation models, especially in the natural language and vision domain. These models have the characteristic of having a very large number of parameters, usually in the scale of billions or even trillions nowadays. And what we've seen from this image is that most of these big models have been contributed by industry. And also a large number for collaboration between industry and academia. And the thing is, or the concern is that these big models are always associated with a very large energy consumption as well. Then I think we as a community should ask ourselves the following question. Do we really need billion parameters, general purpose models for every domain or every task? Because we've seen that nowadays the first solution that most communities have in mind, okay, we have now these big models, let's take one, let's use it, let's fine-tune it, let's do things with them, but these models will solve our problems. So are we using them because they are really needed or because we don't want to miss the wave? And don't take me wrong, because I don't say that these foundation models are not useful or they shouldn't be used, but first we have to think if the design and the way we are using these models are really according to the constraints of the domain we are working on. So today, this morning, we saw this domain. We are working for a few years in the drinking water domain. And in the Netherlands, we have 120,000 kilometers of pipes that we need to monitor to ensure that when you open the tap, the water flows. But as Hester explained today, there are a lot of issues or a lot of problems happening underneath the nice views of the streets and buildings in the cities. So, in our domain, the structure of the data is completely different than text, images, or tabular data, for example. We have, naturally, the water networks are represented as graphs, where the nodes of the graphs are our houses, and the pipes connected our houses are the edges of these graphs. Then the intelligence of the foundation models, at least in our case, has nothing to do with understanding the language, but on understanding the relationships between the properties of nodes and pipes in the network, and also how these signals propagate through the graph. Then the question is, do the same inductive biases that we have in existing foundation models work for our domain? So we think not directly, at least. If we want to use them, we have to adjust them in many ways first, and then we have to test if they work. So we started working on models that are specifically intended for graph structure data. So one of the problems that we tried to solve at the beginning was reconstructing the state of the network. In the water domain, the the main issue is that we don't have fully observable data. So it's we based on few existing sensors in the network, we have to know the state of the entire water distribution network. So we thought that the natural approach would be to use a graph neural network model that help us to do this reconstruction. And then we came with our first model. It's called GATRES. This is the main block of our model. It's composed by two graph attention networks, which are similar to the attention mechanism used in LLMs. But in our case, instead of attending every other element in the context, we attend the neighbors of a specific nodes. So that's the way how this attention mechanism works in our case. And with this main building block, we compose various of these blocks similar to what is done in other domains. And we apply this for predicting or reconstructing the full state of a network. We follow, let's say at the beginning, the traditional approach. We have a network, we train on that network, we mask 95% of those nodes, and we try to reconstruct these masked nodes based on the existing input. We do this through a graph neural network, as I said, and we test it after the model is trained on reconstructing the pressures. So it worked. We train and evaluate our model in the, let's say, in our networks, in the public networks, but we also tested on a real water network from Vitens, which has around 5,800 nodes. And as you could see from the image, the reconstruction error was quite low. So the performance of the model shows that it works. But what is the main issue here, or the problem, the first problem that we found here? Perfect, we have a working model, but then a new network comes in, we have to train again the model for the new network and test it again. A new network comes in and we have to repeat this process. So at the end, we end having one model for one specific network that we need to evaluate. So the next step was how to make this model more generalizable. How to create this model and make it or use it in different networks. So our first approach was, let's train this model, instead of training on a single network, let's train it on multiple networks and then test on the target one. So we train this model on 3 networks, which have different topologies, so the structure of the graphs are different. They have different numbers of nodes and edges. And then we test this model directly on Osterbeck network, on the new target network. So our baseline was a model trained on Osterbeck and test on Osterbeck. With that model we had 1.93 absolute error. Then the first test was zero-shot inference, so without the model seeing any topology of Osterbeck or any sample from Osterbeck, we directly tested on it, and we got a 3 mean absolute error, which is not excellent, but it's still not that bad compared to, or looking that the model never seen this network before. But then with a little fine-tuning, we fine-tuned on this new network, and we actually got better result than the model directly trained on this network only. So let's say our generalization approach shows that work somehow. But then how to improve this generalization? How to make it more transferable and apply in this, at least in the water domain? So then, here's the first approach to graph foundation models for the water domain again. So we are not talking about a general purpose foundation model, but a foundation model that can be applicable in the water domain. What we realize is that the models trained on a single network learn only the hydraulic relationships in the graphs. So they learn the hydraulic part. But we think, what if the model can learn also the patterns in the topology of the graphs? So then we create, or we propose, that our foundation model should be trained on the hydraulic part, but also to somehow learn the structural properties of each water network. So we propose a pre-trained strategy that the model reconstruct node degrees and neighborhood node degrees, which is the sum of the degrees of the neighbors. And in this way, the model could learn these structural properties hidden in the graphs of the water networks. So we trained this model, but for training this model, the first thing that we need to train a foundation model is data at scale. So we first have to work on the data set. This data set was also presented to you this morning. We created a data set collecting 36 water distribution networks which are publicly available. And then we create 1,000 scenarios for each network, which comprises around 2 million water distribution network states. And this data set has been used for training of the model. As was mentioned this morning, we have more than 100,000 downloads. I think this number increases from yesterday to today, which is good. And then when we have this data, we train our model on 20 of those water networks, going from small networks of 19 nodes to 1,900 nodes. And then we evaluated this model on 8 real water distribution networks from victims again. We have networks where we have 288 snapshots or 96 snapshots. We took one of them for fine-tuning our model, one of them for validation, and then we test on the rest of the snapshots that we have. And as you could see, the performance of the model looks quite good in all of the networks that we tested on. So at this point, we went from a single model per network to a foundation model that can be directly used to predict on different topologies that didn't use during training. But now that we have this, can we make it more efficient? So we didn't start with sustainability in mind, but it was kind of the natural evolution of our path. And after we have this, we started working on this idea. And then the first thing, if you see the number of parameters in our model, it's like a toy. It's 1.4 million parameters, which compared to the large language models is really nothing. But don't get confused, because a small parameter count doesn't mean cheap training. So with this small model, we saturated an NVIDIA A30 with 24 gigabytes of RAM using a batch size of only 64. We had available an H100 with 80 gigabytes of VRAM, and we could go only to 192 batch size. So this very small model can actually saturate a huge GPU. Why? Because in our context, in our domain, the context, like similar to what is used in LLMs, depends on the size of the graph. So it also involves the number of nodes, the number of edges, and if you think that we are working with nodes with, let's say, 5,000 plus nodes and edges, this context is quite big. And that's why we end with this situation. So we think, or we propose, there are a lot of compression techniques for making the models smaller. There are efficient adaptation techniques. And we think, can we use LoRa, log rank adaptation, in such a small model, and can we get some benefit? Because these mechanisms were created or designed with models in the billion scale parameters in mind. But if we think that we only have 1.4 million, is this mechanism still working on our models? So we run different experiments on them. So we took as a baseline a single model baseline. So let's say we started with a single model trained from scratch for every target network. That's our baseline. Then we have our foundation model pre-trained on the 20 networks that I mentioned before. And then we have our foundation model adapted with LoRa. And this model freezes all layers but the linear ones. So basically we freeze everything that is not linear, and we apply LoRa on the linear layers of our model. So the heads, the prediction heads, and some other linear layers in between. And in these 3 experiments, we had 10K samples for training. That was our budget. So to be, let's say, fair with the comparison, we went with the same 10K for all the experiments. But we wanted to see if we can reduce this training budget if we apply LoRa on this. So this is the 4th experiment that we run, and then we check what happens with performance and what happens with energy consumption in all these cases. Another detail here. So in these experiments, the baseline were run for 100 epochs, and with LoRa, thinking that when you fine-tune or adapt your models, you have some metric in mind, so you decide if you stop it when you get certain error threshold. We apply early stopping, and we stop at 50 epochs only when we have this adaptation technique. So this is our first results related to energy performance trade-off. And as you can see, in the x-axis, we have energy consumption. In the y-axis, we have the mean absolute error of our model. As you can see, in all our cases, in all our experiments, the energy budget is lower with the adapted models, and the model get a better performance very early. So as you could see, the best performance of the baseline model consumes, for example, in this case, around 87, if I remember correctly, of watts hour. But you can see the performance at epoch 20 was already much better than the performance of the baseline. And this is happening like consistently in all our experiments. Here, for example, the difference in energy consumption is, or no, here is small, but the performance still is winning. And then one first question here is when to stop training. Because here I'm training just for the sake of comparison, but if you can see, I could have stopped training at, I don't know, here at this budget. And I get already better performance than the baseline. So this shows that having a foundation model and adapted in the right way can give you benefits in performance, but also in energy. And as you can see, at least in our experiments, we don't need this trade-off of should I compromise performance to get some energy or vice versa, but we are always getting gains in energy, but also in performance. These are other metrics that show this, as you can see here. This is our mean absolute error. The blackish color, sorry for the word, I don't know how to, I don't know if close is good here, but then we have, as you can see, in all 7 cases, the performance of the adapted model with LoRa is much better. Then we have here, as I mentioned, the experiment when I reduce the training budget, and of course we lose a little bit of performance, but we always win against the baseline. So it means that if we have a very small training budget, we can still get some benefits following this approach. The same happens for the R-squared coefficient. Here is, as you can see, in most cases is quite similar, but there are some cases where the differences are noticeable. And this is the energy consumption. Here is some also important or interesting information. Of course, we shouldn't discard the training energy consumption, because this is the watts hour that cost training the foundation model, which is large compared to the rest. But here is the thing, the gains on sustainability, on energy, comes from the reusability of our foundation models. As you can see, the gains are large, and the more we reuse our model, the more this cost pay back in the long term. So this shows that our approach can give us a sustainable way of having good performance and achieving the goals that we need. But the key is to introduce the right inductive biases, to introduce the right architectural mechanisms that the model needs for the domain that we are working on. So these are the takeaways. The sustainable AI is not only about compressing huge model after we overscale, but it's about designing reusable, structurally appropriate, and cheap to adapt from the beginning. So thinking always in the constraints of the domain. Another thing, as you could remember, not always a small parameter count mean that it's cheap. And energy performance trade-offs were not observed, at least in our experiment. So it's something that needs more exploration, but at least shows that for this domain, we can have good performance models, but also energy efficient. Thank you very much.
Questions?
Thanks for the interesting talk. It's very promising to see that the sectoral models, and especially maybe graph representation models. My question is very simple. Do you feel that your approach for graph-based GNNs can be also applicable as similar approach to the other domains like energy and other critical infrastructures, for example, with some tuning, but is it generalizable? What do you think?
Thank you for your question. Indeed, we have been thinking to test our approaches in other domains, and energy, of course, is one of the more directly comparable, I would say. Can be also applicable, for example, in gas, and even not only physical infrastructures, but I think they have been also applied already in, for example, transportation networks. So the models are applicable as long as we have a graph representation of our data. And if it's naturally in that way, like in the case of water networks, it's even more like, let's say, straightforward, the transferability to other domains.
Yeah, many thanks for the nice talk. My question is, how do you interact with your model? Or how do you use your model? Yeah, what's the interaction example for? Yeah.
Well, in our case, there is no, let's say, direct interaction like we do with prompting or this type of language models. In our case, is the use case at the end is more in the, I would say, traditional way. So you have well-defined inputs, which in the case of our use case, where the pressures at each node in the network.
You input the sensor values, right?
Exactly, yeah. So we input the known values, and then the model predict what is missing.
Well, you have 5,000 nodes. Does it predict for every single node, or you just say, give me the pressure at that point?
Our model predict at this point for all the networks, so for all 5,000 nodes, given 5% of them. But you can also choose some specific nodes if that's the use case, and the model will give you that answer as well.
Okay, and you were saying that the topology that you teach the model is generic?
Is not generic, but is public. I mean, it's not from Vitens, for example. It's not a real, not a real, well, I don't know how to use the term real or not in this case, but let's say our networks, our training data is publicly available water distribution network. So everyone has access to this, and we created data on those specific water networks.
Well, that I understand, but what you actually teach your model
Mhm.
is about topology, right?
We teach both together, topology and hydraulics.
Well, I want to forget about hydraulics. What do I have to do?
You have to find what is the right pre-training task for your domain. So for example, what we wanted to learn this is the patterns in the topology. And we think that
So you don't learn topology, you learn that the next node with respect to pressure is this and that, or
that's the
you
what
do not separate clearly.
exactly. Yeah.
Okay.
But it's joined in the at the end because it's the sum of both things what the
Okay.
model actually adjusts and updates in the learning process.
Okay. Thank you.
And probably I can just add to the answer. So what's really learned is the message passing. So for each node, you learn the role, how other nodes around you influence you. So you kind of learn the context. And then of course it will be very easy if it would just be your neighbors, but neighbors, neighbors of your neighbors, neighbors of your neighbors. So you have this transitional and similar like large language models work.
Let me add, can you, if for example, somebody is saying, don't use my network anymore, can you forget it? One of the trained networks, it's somehow represented, right? And now somebody says, oh, that was wrong data, I fooled you, or give it back to me if it is another kind of network that I don't want anybody else to use.
I would say that's not an easy task to do because it same happens with language models.
Yes.
So basically, if you don't want to use that data, you have to retrain without them. But it's not a natural way to just forget this and let's continue using it.
Thank you.
So given timing constraints, I would suggest we continue. Let's thank the speaker again.